Okay, so thanks very much. So I'm back. So I want to show you the second part of my presentation, and this is work in progress in some of our latest results. So first, selenium, an ecologically important trace element. Again, work from Mark Donner. He's done selenium speciation, and this is dissolved selenium in the Athabasca River. And he's found that the selenium concentrations are low, and selenium is not significantly more abundant downstream of industry compared to upstream. So that's Mark's work on selenium. We also have been working on total concentrations of metals in water. So some people want to know the total amount that's in the water. And again, this is Babar's work, and he's collected the particles that are suspended in the water, and those particles are digested and analyzed. And again, you can see the concentration of lead is proportional to the concentration of thorium, which means the amount of lead in those particles is exactly what we would expect. So the slope of this line is exactly the same as the Earth's crust. So the amount of lead in those particles upstream and downstream from industry is the same, and it's exactly what you'd expect. It matches crustal values. We've also been looking at trace elements in fish. This is some work we're doing together with Mark Posch. The trout perch is a very small fish. It's a non-migratory fish, so it's been collected at different stations along the river. And we've been analyzing the ear bone of the fish, and we've measured a long list of trace elements in the ear bone of the fish, and they are not significantly more abundant downstream of industry compared to upstream. And in terms of the colloids that are in the water, these natural nanoparticles, Marjan is a master's student who's working on these with Chad. This is an example of a fractogram doing the size resolved analysis. And this is actually really cool. She's looking at these particles using the transmission electron microscope. And you can see on the right-hand side the scale bar, 100 nanometers. And these are particles of iron hydroxide that Mother Nature is adding to the river. So when the tributaries streams come into the river, they're bringing in a lot of dissolved iron, and that dissolved iron is actually in the form of nanoparticles. And this work is funded by NSERC. One of our goals is to better understand spatial and temporal variation. So this is the Horse River where it enters the Athabasca River. This is upstream of Fort McMurray, and you can see the amount of iron and DOC coming into the Athabasca River from the Horse River. And we want to know how much does this impact in Athabasca River. So we can see all of that organic matter trailing down the Athabasca River. So Tommy Nurnberg, he's the engineering mechanic on our team. It's kind of a mechanical genius. He's built us this sampling device so that we can sample the water at any depth in the Athabasca River. This is really cool, built of surgical stainless steel, all cleaned in acid, reassembled. And this is a depth profile across the Athabasca River. So now we're measuring trace metals as a function of depth and trace metals going across the river, and not just their concentrations, but their speciation. And again, funded by NSERC. We're starting to look at contaminants in country food, so specifically trace elements. And we've started by looking at some of the berries that we find in our peat bogs, cranberries, lingonberries. Samantha Statue doing her master's in these berries. And this is a look with an electron microscope at dust particles on the berries near one of the open pit mines. So Samantha, in the work she's doing, she can distinguish between trace elements that are actually in the berry, like copper and zinc versus elements that are on the surface of the berry, like aluminum, for example. And then Melissa is doing a master's thesis on trace elements in liver and kidney from beaver. And her work has started with liver and kidney samples from a moose that was donated by a friend at Fort Mackay First Nation. But it turns out the liver and kidney of the moose are really quite clean as regards trace metals. So we've had to modify our digestion procedure in the clean lab to be able to digest enough material to be able to measure some of these trace metals. So to summarize, it's very important, if we want to understand trace elements in the environment, it's very important to understand the geology, and then it's very important to understand the chemistry of the individual elements, and of course, biological transformations. And underpinning all of this is high quality analytical data. And one area where we are uncompromising in our lab is the quality of our analytical data. It has to be accurate, it has to be precise, the measurements have to be sensitive, and we must have low limits of detection. These instruments in the lab don't run by themselves. We have a great team of people that are working on all of these things that I've shown you, and I'm grateful to them for all of their hard work. And then the sponsors of our laboratory, the people that helped us to create the lab. Alberta Innovates has supported all of our work on atmospheric deposition, and Alberta Innovates with COSIA has supported our work on the Athabasca River. And as I said recently, we've got funding as well from NSERC. Thank you very much for your attention, and I'm happy to take any questions. Thanks very much.